Greetings, everyone, from wherever you are joining us. That could be good morning, good afternoon, or good evening. My name is Dave Cadu, and we will be starting the webinar in just a few minutes. I just wanted to give folks a few more minutes to join the webinar. If they set their reminders for 10:30, then they'll be fashionably late. So appreciate it if you just hold on for a couple minutes and get started. While we're waiting to get started, I just want to remind you that IWCS has a new website that we launched earlier this year, and you can find access to technical papers, including this one, on the website, and also the webinars, previous webinars, in case you've missed those. So we encourage you to go wander around our website and get the various information that you're looking for, and then also to learn more as we start populating information about next year's conference in Providence, Rhode Island. We're looking forward to being in person at that conference, so fingers crossed. So we'll give folks just one more minute. If you did not join our IWCS 2021 virtual conference, you'll note that this platform that we're using for these webinars is essentially the same platform that we used for the full virtual conference. So it was very effective this year. For those of you who did attend, we thank you for doing it. Okay, so it's time to get started. Let's go ahead and again, I'll welcome you. My name is Dave Cadu, and I'm honored to be the CEO Director of IWCS, and I'll be your moderator for today's event. Just a few housekeeping items. As an attendee, you're part of a larger audience, so during the presentation, all participants will be in listen-only mode. So what we need to do, if you would like to ask questions or make a comment, I ask you to submit your questions and comments in the chat box. It should be on the right of your screen in the platform, the IWCS platform. So you type it in there. Try not to put it in the chat function in the Zoom. If any of you are watching in the Zoom mode, we prefer you to put the questions so we can record them in the chat function on Pathable. Also, this event is being recorded for rebroadcast as a reminder. Today we welcome Mike Gurreri from CommScope. He is a distinguished engineer in the network connectivity group. He's located in Pennsylvania, USA. Mike will be presenting his paper on the review of connector end-face scratch recognition and verification study for automated microscopes. This presentation was presented at the conference a few weeks ago. Very well received, an excellent paper. Mike received his Bachelor of Science degree in Mechanical Engineering from the MS Engineering from Pennsylvania State University. And let me just, I forgot here to share my screen, so let me just do that real quick here. Just bear with me for a quick second. All right, there we go. Okay, hopefully, Mike, can you see that?
I can.
All right, excellent. Sorry about that. I was meaning to get this up and running. But again, Mike graduated the BS degree in mechanical engineering in 1997 and his MS degree in engineering science from Pennsylvania State University. He joined CommScope through the divestiture from TE Connectivity and prior AMP. In 1998 as a product development engineer in the fiber optic business unit, taking on various management and technology development roles throughout his career. Mike is currently a distinguished engineer in the network connectivity segment of CommScope and is a U.S. delegate to IEC SC 86B, where he received the 1906 award for contributions to multifiber optical interfaces. Mike holds over 50 U.S. patents in the field of fiber optics and was named a CommScope Master Inventor in 2020. So he's been a busy guy. So we appreciate Mike being with us. So welcome, Mike. And, thank you for your presentation this morning.
All right, hopefully you can see my screen okay. Good morning, everyone, and thanks a lot, Dave. I really appreciate the introduction and the opportunity to present this webinar today. So over the past few years, IWCS has really emerged as one of the leading forums for optical connectivity contributions in the industry. And I hope this work adds to the excellent collection. In this presentation, I'm going to highlight the results of a round-robin study on connector end face scratch inspection systems that utilize automated detection methods. Much of this work was carried out as a task group within IEC SC 86B in conjunction with experts really from around the world. It was quite a diverse collection of people, consisted of multiple equipment manufacturers, connector manufacturers, end users, and people from academics. And so with that, guess I'll give you a little bit of background on the magnitude of the challenge. Consider that millions of links in a hyperscale data center are installed, service provider technicians deploying drops to homes, or even the shift supervisor of an assembly house that's trying to ship patch cords on a Friday afternoon, which certainly is relevant given the supply chain challenges of today. In all these situations, they're really gambling on the accuracy of their inspection equipment. So it's been a long practice to clean and inspect an end face during installation, typically as part of the validation process. But apart from that, apart from final deployment, interfaces are also routinely inspected, for instance, after polishing, prior to end-of-line manufacturing testing, as part of quality control programs, and obviously during network troubleshooting or maintenance. So within, I'd say, probably the last decade, automated inspection systems have emerged where a digital image is acquired. It's analyzed via an algorithmic process and then compared against pre-programmed acceptance criteria that really judges it from a pass-fail standpoint. So these automated systems, they really offer the promise of eliminating human subjectivity that's associated with manual detection. For instance, uncontrollable variables like the technician's eyesight, focusing ability, lighting conditions, installation environment, and even their experience could impact reliable and repeatable results. However, automated systems are prone to other sources of variability, like system hardware differences, imaging processing methods, and detection software that can all be sources of measurement uncertainty. So we really undertook this work to investigate the variability of state-of-the-art systems, and it'll serve as a benchmark for further improvement. So in this presentation today, I'll first review the inspection methodology that was used. I'll try to highlight some of the acceptance criteria and test details. We'll then discuss the sample groups, important parameter differences, and how they were fabricated. And then finally, highlight some notable outcomes of the round robin that will be analyzed, and finally then summarize the conclusions, along with give some recommendations for future work. So the round robin study consisted of multi-mode and single mode samples in the single fiber LC format, as well as a multi-fiber MPO. The samples had various end face conditions, which I'll show later. We worked directly with the microscope equipment manufacturers, where they anonymously recorded scratch counts and provided that information. There were 8 single fiber manufacturers and 5 multi-fiber participants. We limited the study to just test gear makers, and that eliminated sources of noise from users such as non-calibrated instruments, maintenance issues, or not having the latest software updates. So to look at the measurement reproducibility, each sample was measured 3 times. And the LC samples, which have a cylindrical axisymmetric ferrule, we rotated those samples 120 degrees between trials. The pass-fail criterion is defined in IEC 61300-3-35. So that was used for the evaluation. And this really provides requirements in 2 inspection zones, Zone A, which you see, and then Zone B. So Zone A is centered on the fiber. It encompasses the core area. For single mode, the diameter is 25 microns. Multimode, the diameter is 65 microns. And then Zone B is this annular ring that goes from Zone A out to a diameter of about 115 microns to capture the cladding. The scratch width limits are depending on the fiber type. So for single mode, such as G652 or 657 fiber, basically any detectable scratch in the core region in Zone A would be unacceptable, while in Zone B, scratches greater than 3 microns would be considered significant. And then multi-mode, Zone A scratches, the requirement would be greater than 3 microns in width, and the cladding region, Zone B, greater than 5 microns in width. So using these criteria, the participants individually made their measurements for each sample, and then we had tabulated the results for scratch counts. So I'll first discuss the multi-mode samples, which had 8 test groups. 4 were with the LC 1¼ millimeter ferrules, and then 4 with the MT ferrules. Each group had contained 3 samples, so a total of 24 samples were evaluated. These were further subdivided into whether the end face had light scratches, which shouldn't be counted as being significant, or wide scratches that exceeded the criteria. It was really set up as like a factorial type design of experiments, where we had some combination of light and heavy scratches for each of the ferrule types. And so over the next few slides, I'll share the actual end face conditions of the samples. So we started with a control group, groups A and E, they were really considered to have pristine end faces. There weren't any perceptible scratches. So that was kind of our baseline group. Then moving on, samples were produced with typically 1 to 5 heavy scratches across the end face. So these scratches were produced by introducing a 5 micron diamond suspension during the final polishing step. I can tell you it was a fairly random process and very laborious, where we had to basically create a lot of specimens to find representative candidates for the study. And then the next two groups had many light scratches, or almost like a cross hatching across the entire end face. I know these kind of look like they've been scuffed with an 80 grit sandpaper, but they were actually fabricated by doing a final polish with a 1 micron diamond film. So these light scratches would be basically should not be counted as significant. And then the final multimode test groups had a combination of light scratches as well as heavy scratches. So this really requires the inspection system to differentiate between countable and not scratches. So prior to circulating the samples to the participants, multimode return loss was measured against a reference using an 850 nanometer encircled flux launch. The LC samples with pristine end faces were in the mid 50 dB range, and the MPO were also in the upper 50s. So test group B, which had a few heavy scratches, showed maybe a 5 to 10 dB difference compared to the control group. However, the samples that had many light scratches showed pretty substantial degradation in return loss, about 20 dB. This could possibly be to the cumulative influence of all the defects, or possibly the formation of a high index damage layer during polish. And then similarly, the multifiber MT samples, there was also about a 20 dB difference in return loss for the samples that had many light scratches. The group that had just a few heavy scratches really showed no degradation compared to the control group. So one important takeaway here is that, even though the samples look pretty bad, they still meet the return loss requirements of most application standards, which is about 20 dB. I'll also say that attenuation is typically not really influenced by scratches. So the metric to use would be reflectance. So I'm going to now move on to the single mode test groups, which like the multimode samples, we had LC and MPO connector formats. The end faces were binned into categories which had either 1 to 3 scratches that passed through the core or passed through zone A without intersecting the core. And the reason for this delineation was the expectation that contrast differences between the core and cladding, may impact the measurement results. So like the multimode, we also fabricated a control group that really had a pristine end face. There weren't any perceptible scratches when you viewed them with 400x magnification. And then groups B and E had at least 1 scratch in zone A. These were approximately 1 micron in width, and they were verified using an atomic force microscope. So the scratches are extremely faint, and I suspect most of you won't even be able to see them on your screen. So what I've done is I've tried to superimpose where the scratch was. So you can see that these intersect with zone A, but don't directly pass through the core. And then similarly, what we did is looked at samples that had scratches that passed through the core region. And again, you can see that they're really light, and they really stress the resolution of the measurement system. So like the multimode samples, we also characterize single mode return loss. This is at 1550 nanometer wavelength being shown here. So the LC UPC samples, they were typically in the 57 dB range for the Pristine group. Then samples that had scratches typically suffered about a 3 dB drop in return loss. And from experience, I can say that this is pretty typical, where if a scratch is introduced at the interface, you see about a 50% increase in reflectivity. The MT group actually had an 8-degree APC interface. So that really limits the ability to discern the reflectance of the various samples. So we didn't really see any impact for the MT samples. I'm going to now transition to review the results of the round robin and try to highlight some of the findings. We'll start with the multi-mode samples in the next few slides and then move on to single mode. So in this plot, what you can see along the x-axis is the number of scratches that were reported by each participant. And there are clusters of 3 data points that was representing each trial. So basically, what you see is, 5 out of 8 manufacturers consistently counted 3 scratches. But there were also 3 participants that counted between 0 and 1 scratch. And this is another example. This was a sample that had very light scratches. You can see that roughly 25% of the participants tended to over-report the number of significant scratches. While most of them, 75%, didn't really identify any scratches, as would be expected. And this was a sample that had both heavy and light scratches. You can see there's really considerable variability here. For this sample, scratch counts between 0 and 8 were found, with about 40% of the participants seeming to underestimate, with 3 out of 8 not identifying any scratches at all on this sample. So there also seemed to be lower reproducibility within the equipment, and this potentially could be related to the scratch orientation changing for the LC sample as it was clocked 120 degrees between measurements. So similar trends with the MT samples. So this was a sample that had heavy scratches only. The scratch count ranged between 0 and 4, depending on the participant. And, this is another sample that had heavy and light scratches. There's still a little bit of variation between inspection gear, where the measurement repeatability does seem a little bit better for particular instruments compared to the single fiber. And maybe this is because the MT samples weren't rotated between trials. So I'll now move on to the single mode samples. For a single mode, there was, really, I'd say, poor correlation between pieces of equipment. So keep in mind that any observable scratch in zone A, regardless of width, should be counted for single mode. So here I can clearly see 2 scratches, but it seems like largely there's a tendency to underreport scratches, with about 60% of the participants not counting any scratches at all. Although one participant did identify between 3 and 5 scratches. The single mode MT samples also followed a similar trend of underreporting scratches. So in this sample, I clearly see 1 scratch, and one of the participants, participant R, did identify one scratch, but the other 4 didn't report any scratches. So, in conclusion, the findings of this study to me were really quite eye-opening. It shows significant variability between commercial equipment, but I think it serves as a benchmark of the state of the art. So we tried to be very systematic in exploring a multitude of parameters that could impact measurement uncertainty. So, in general, while there was poor correlation between the hardware, individual system repeatability, to me was fairly reasonable. So I suspect that calibration artifact that would be globally available, along with, standardized certification procedure, could really help improve the robustness of these systems. And I wanted to conclude this presentation giving a minute to recognize my co-authors. Josh Webb, he did an amazing job fabricating these samples and doing a lot of the analytical work. Dr. Tatiana Berdinsky, she's the founder of Novo Photonics with more than 25 years of experience in fiber optics and optoelectronics. So she was the leader of the task group. And then finally, Ton Bolhar and Daniel Dame. So Ton is the secretary, Ton is the chairman of the IEC SC 86B Working Group 4 committee, and Daniel is the secretary. They both really provided considerable support. And also wanted to sincerely thank the participants of the study who really made this possible. So really, the first step in improving is understanding the problem. And I think the group really continues to make excellent progress on this front. So looking forward to the future. So with that, I'd really like to thank everyone and open it up to any questions.
Mike, fantastic. Thank you so much for that informative presentation. I'll remind everyone that you have now an opportunity to enter your questions, and you can do so by typing in your question in the chat function and then hitting the send button. As of this moment, I don't see any questions, but we'll give you a moment to type in your questions. Mike, do you see a lot of work going on within IEC on further improving quality and inspection procedures and processes as we go forward, particularly?
Absolutely, yeah. There's quite a bit of activity related to calibration artifacts, where we're, the equipment makers are really trying to make sure that their systems align and give the consistent results among, different systems. So a lot of good work there that's being done.
Well, that consistency is important because, more and more as we integrate, everything in the smart environment, and, with the incredible broadband expansion that we're going to have, we're going to want some consistent testing and quality. And so appreciate the fact that you've got a good team internationally and globally to address these issues so the manufacturers can be consistent, like you said.
Yeah, there's also, Dave, a lot of work going on related to kind of use cases, I would say, where one of the primary failure modes in the field is dirt or debris at the interface. So some of these systems are moving towards being able to identify in a kind of a wide field of view whether or not there's debris at the interface. So that certainly has a much bigger impact in terms of optical performance compared to scratches. So seeing kind of a shift of really addressing relevant failure modes that are common in the field.
Yeah, and that field infrastructure is changing. I mean, you got a lot now where there's a lot of patch systems, and you got equipment and devices and applications down at the end of the the end of the line, the edge computing type of stuff. And so there's a lot of work to be done as we expand into the future, to connect everything.
Yeah.
So,
Yeah, we really want to make fiber as seamless as copper, when it comes to deployment. So.
Well, there's no doubt that, fiber is certainly going to be a major force. Let's not forget copper. There's going to definitely be a role for copper to play. But in order to achieve some of these objectives that we have, fiber is going to be everywhere. And we've got to make sure that these inspection techniques are consistent. So do you think that these automated systems, if developed further, could eventually be used to optimize the connector manufacturing process rather than just an inspection and rejection mode? So what effect does it have on actually continuous improvement?
Yeah, absolutely. I think there's a lot of opportunity, for these automated systems to, optimize, polishing process development and, manufacturing line testing. So I think they're really well suited for that environment.
Yeah, agreed. Are there plans to do similar studies for contamination and debris detection?
Yeah, there are. Rather than just scratches, the team is also looking at pits and other types of defects. Contamination, just because it moves around, can be a little bit challenging, but that could be another area.
Right. Okay. If you have any further questions, just enter them, but we'll go ahead and wrap up now. And again, I want to thank Mike sincerely for presenting this very interesting and important topic today. We do have some contact points. Let me go ahead and share those for you so that in case you want to reach out to Mike directly, you can do so.
Dave,
yep.
Before you advance, I just want to let you know that we have a new question in the chat.
Excellent. Okay. All right. Why don't you go ahead and ask that?
Okay. Mike, the question is, did you observe the three-dimensional glass structures by your atomic microscopes? And did you distinguish the variations of return loss values?
Yeah, it's a good question. Certainly the AFM gives a three-dimensional profile. And off the top of my head, I can't really define, what the depth would be compared to the width. And we do have the data on that sample for return loss. But unfortunately, I don't know off the top of my head. I think the samples that had scratches had about a 3 dB degradation in return loss, but it would be certainly interesting to correlate that better. I certainly agree with the question.
Okay, thank you, Mike.
Thanks.
Yeah, thanks, Becky, and keep looking if there's any last-minute questions we can get to them. But again, please note the contact points here that shown on your screen. And Mike would be very willing to receive any other questions or comments offline. Again, these IWCS webinars are recorded and they will be archived on our IWCS.org website. It normally takes a week or so to get them up. So if you want to revisit this and the other webinars, feel free to do so. The IWCS webinar series will conduct technical paper presentation webinars along with sponsored company events several times each month going forward. We have some sponsor spotlights and exhibitor spotlights that we'll be sharing in the future in addition to these technical presentations as well. Our next scheduled technical paper presentation webinar event will be on Friday, December 17th at 10:30 a.m. Eastern USA. Each of you will be receiving an announcement for the event. So feel free to sign up and also share these announcements with your colleagues so that they can join and register as well. We'll endeavor to have topics such as connectivity and optical fiber applications, along with copper and materials in the coming months as well. So stay tuned. Let's check any last questions, Becky?
No, I do not see any further questions, Dave.
Very good. Well, we thank you for joining us, everyone. And before we conclude, I think it's important that we all recognize and thank the IWCS partner sponsors who contribute greatly to the success of our cable and connectivity industry forum, both in real content, as you saw here today, CommScope, but also financially to help underwrite the success of IWCS. Without their strong leadership and generosity, we would not be able to bring these important technical innovations and information to you and our global community. So again, we thank you to these leading suppliers for our industry for your support. For over 70 years, IWCS Cable and Connectivity Industry Forum has been the recognized leader, showcasing new technologies in cable and connectivity products, processes, and applications. And with perseverance and a high level of confidence, our next 71st annual Cable and Connectivity Industry Forum will now take place live on Monday through Thursday, October 10th through the 13th in 2022 at the Rhode Island Convention Center in Providence, Rhode Island, USA. Please watch your inbox, social media, and our website to learn more about the exciting information as it becomes available. And so visit iwcs.org for more information. Again, thank you for your participation. And Mike, we can't thank you enough for bringing this to us. And this concludes today's event. Thanks, everyone. Have a great weekend. And for those of you in the US of A, happy Thanksgiving.